can't remember the name.
Yeah. Okay. So we've been covering turbines in general, and looked at a motive turbine. Now we're sort of inside a power plant. So the as you can see, these things are large. This figure is figure 620. So it's one set of turbine blades for a 1,000 megawatts. This is a gigawatt plant. 1,000 megawatt tandem compound steam turbine. So the blade itself on the right is a meter long. You can see the workers standing next to them. It's about the entire machine is between 8 and 9 feet in diameter. So they're sort of lifting this or placing it down into place to put it into service. Okay. So we're talking a little bit about why the downstream blades are a little bigger, a little deeper. The higher pressure blade is or turbine is smaller. Then as the steam expands, it's still hot. There's still energy left in it, so that goes into a larger turbine, and we can see that then can be sent out in two separate directions into yet a larger turbine. The irony here is the larger the turbine gets, the less power there is from it. It's sort of the law of diminishing returns, if you will. But at some point you're like, okay, 3's enough. There we go. So the top is called the tandem. The tandem compound. Compound is meaning there are multiple, and they're in tandem because they're all in the same shaft. The one below is called the cross compound, where you have separate generators. So here's the turbine. The generator itself is a magnet and wires spinning, making electricity. Okay. A few other things worth noting. There's the boiler system. I'm just looking at page 203. There are it can be these devices called superheaters, which will get the steam hotter and more pressurized, so the efficiency goes up. The reheaters, which the steam revisits the boiler in between successive turbines. So you might have a reheater here, give it a little more heat before it gets sent into the turbine. Hot flue gases may pass through another air preheater to heat the incoming air, or an economizer. So the economizer is basically saying let's bring the air in at a higher temperature, so we're not spending all the energy just getting the air up to temperature. So a lot of different ways to play with the thermodynamics coming into the plant. Okay, and then the condenser. I think there's a shot of a condensing. So here's a big condensing tower. So again, here's just water coming in, and this was a big deal this summer in Coldstrip. There was some water rationing because this water has to come in or the plant cooks itself. I mean, it needs that cool water coming in from from Mother Nature. Sprayed into the air to evaporate, and then it's just returned to the power station. So all the turbines and boilers are all over here, and then here comes the warm air, and then it's just kind of there's your completing your Carnot cycle. So the cold portion of that Carnot cycle is here. So you just got a big big cooling tower. That's all it is. And so you're like, is that smoke coming off? No, it's just sort of low grade steam. Okay, so here's what what the plant, schematic of what the plant might look like. So at the top, we have coal coming in, 200 tons per hour. Coal strip on a steady state day burns a coal car every 5 minutes.
Train car?
Yeah. Every 5 minutes, one of those bad boys disappears in the coal strip.
Jeez.
Goes up in the air. and that's just coal strip. I mean, that's just one power plant in little old Montana.
Oh.
So that's the rate. I think one problem I like doing near the end of class. Maybe we'll even do it here. What time was it? 5. We have until 11. Maybe we'll do the problem today. Yeah, we'll do it today because we're almost at the end of this lecture. The problem we're going to solve. Yeah, let's just do it now. The problem we're going to solve is we're going to start out with let's just do it. Let's quit talking about it. This is because we've already covered all of this. We know that coal and air come in. Here comes steam. It goes to the turbine, spins a magnet, and you make electricity. Yay. Okay. But this is the problem we're going to solve. Okay. Civilization. This is a good warm-up for the first problem. Civilization. Runs at 16 terawatts. And somewhere, let's just go out and look at, what do you guys think is of the global energy consumption, what fraction is currently coal? What percentage? Is
38%.
38, 40? You think it's 38?
Yeah, because actually I just saw the numbers yesterday in Lisa Swallow's class.
Okay.
And I think it's 38%. Because coal and gas is like 32% or 36%.
Sometimes the EIA has this.
I saw in the paper this morning that the Paris Agreement is going to be enforced almost immediately on November 5th.
Wow, that's intense.
Yeah. It's just two of the island nations and big, polluters, the big polluters of the earth have finally realized that they can't keep going on the same path as we have. So emissions are going to start being strictly controlled.
10% there.
Yeah, I don't. That's.
Oil. That seems to me that they're lumping multiple, like natural gas and liquid gas together in that.
And we'll actually get into this in a little bit more. Coal is a source of energy with the largest growth. I just want a number. I want to see what the fraction is.
I wonder if that's up to date.
Oh, it's Wikipedia. It's absolutely true.
Yeah, it's close enough for our purposes. Well, let's use the 2012 numbers. Final energy consumption refers to the fraction of the world's primary energy that is used in its final form by humanity. In 2012, the world primary energy supply amounted to 155,000 terawatt hours. Let's just see here. Coal, come on, let's find it. Well, looking at 28.9 right there. I would have thought a lot higher. Okay, so oil 31, coal 28, natural gas 21. I think natural gas has just really come online in a
With the last,
Biofuels and waste 10.2, nuclear 4.8, hydro 2.4. Other, I mean, it's astonishing how small those numbers are. If you add up all solar, wind, geothermal, and solar thermal, 1.2%. Okay, but let's go with that 28.9%. 28.9%. 28.9% is coal. And now we just need the energy density of coal. I don't know if I put that in my paper or not, but. All right. Let's just say 30 megajoules per kilogram. Let's go with that. 30 megajoules per kilogram. 30 megajoules per kilogram. Okay, and now we need to know how many kilograms there are in a coal car. And it's something, it's like 100,000 tons or whatever. We'll figure out how coal car capacity, BNSF. Let's just look at the ones that come through Missoula. BNSF railway. Coal train, fact check. One hopper holds 100 to 125 tons of coal. So it's going to depend. So let's just make it easy.
It says use 115 tons right there.
Let's use 115. How about that? That's about right. So 115 tons. Tons. So the question is, if all of the world's coal were on one train going into one power plant, how fast is the train going? That's the problem. So I'm going to pause it and we'll calculate it together, and all shall be revealed. So how fast is the coal train going? That's the question. All right, so I'm just going to pause this. Okay, we're back, and I hope you solved the problem. There's another kind of cool video out there. It's called it's Professor Dave. It's just another professor out there who just goes through chemistry. Kind of cool. I was watching. I learned chemistry is one of those things that I enjoyed but never became as I would like. But it's amazing. There are all kinds of good educational things out there on the YouTube. But back to our problem at hand. What I asked you to do is say if civilization is running at 16 terawatts. I've seen some other figures where it's more like 12, and that our energy consumption has actually peaked in a lot of ways. But we're just going to use 16 for the sake of argument. And we just looked up that close to 30% of that is coal. And we looked up that coal is about 30 megajoules per kilogram. I just made a rough conversion and said that's 30 gigajoules per ton. So you multiply a megajoule by 1,000, you get a gigajoule. You multiply a kilogram by 1,000, and it's a metric ton. So I just use T for metric tons there. And inside that coal car, 115,000 tons, and we'll get into exactly what the different types and flavors of tons are. But again, we're just doing order of magnitude here. So I just said, okay, 115 tons is approximately the same as 115 metric tons. It's approximate. The coal car is 60 feet long, and I just, again, approximated that as 20 meters. So from that, we can get how much energy there is per meter in the car. Energy per meter. So if there are 115 tons in 60 meters, and there are 30 gigajoules per ton, 115 tons per 60 meters times 30 gigajoules per ton becomes, and basically we're just dividing that 115 by 2, the tons go away, and we end up with 57 gigajoules per meter. So of these 20 meters, each one has 57.5 gigajoules of energy. Nice little energy slices there. The other thing to note, though, the energy is not just sitting in the coal. The energy is sitting in the coal plus the oxygen that combines with it when it burns. So that's another thing to think about, is there's all this fantastic oxygen in the atmosphere. That's where the other half, the other portion, or whatever, of the energy is hiding. Or not. It's all around us. Can't see it, but there it is. What?
I read they separated from cooling off the air significantly, like a minus 183 degrees Celsius to remove the oxygen from the air to get pure oxygen
For?
into the cold chamber.
Oh, I have not heard. I mean, there might be some technologies where you're pumping pure oxygen, but typically it's just straight air going in.
Oh, okay.
Yeah.
Gotcha. I just thought they were doing that to remove the excess nitrogen.
Nah, no. I don't. And that kind of gets back to that summary 2 paper where let's get rid of the nitrogen first and just pump straight oxygen. There might be some plants that are doing that, but then again, where's the energy to get rid of the nitrogen coming from? And so you'd have to compress, and that's how these liquid gases are. I mean, it's just compressed air.
Yeah, on site.
Uh-huh.
I saw it in the book in the back of the CCS technology.
Yeah.
A little diagram where they have an air separation.
There we go.
unit.
Air separation unit, yeah.
And they cool it off significantly.
Yeah, and that will help with the NOx emissions. If you don't send any nitrogen in there, then you got the NOx. So, okay, so we're looking at 57.5 gigajoules per meter. That's the linear energy density of the coal car. Okay, so now here's we're running at 16 times 10 to the 12th. Oh wait, yeah, 16 times 10 to the 12th. 10 to the 12th is terajoules, or terawatts. So 16 times 10 to the 12th joules per second. That's your 16 terawatts. Here's your coal fraction, 28.9%. That becomes 4.624 times 10 to the 12th joules per second. So that is the energy consumption rate. So now we have energy divided by time for our consumption rate. And up here we have energy divided by length. We've already done a little bit of dimensional and units analysis. So, stare these down and say, how can I get those two things into a velocity? That's what I asked for. I said, what's the velocity of the train? So, if we do this, joules per second, energy per time, divide that by joules per meter, joules per unit length, we end up with meters per second. That's just your, straight up algebra. And so, you know, if we think about that a little bit, it will make sense because this, this top is the overall rate of energy consumption. So the faster we consume energy, the faster that train is going to go. Now, on the bottom, though, what if we were packing uranium or a higher grade coal? That would allow the coal to slow down. That would allow the train to slow down. So a bigger number on the bottom makes the number smaller. So you kind of look at this for a second, stare it down. Okay, makes sense. I'm ready to move on and pull the trigger. So 4.644 terawatts, which is 4.644 times 10 to the 12 joules per second. The energy density is 57.5 gigajoules. That's times 10 to the 9th joules per meter. So that just falls out. 4.6 divided by 57. And again, this is one of those problems where you're really doing 3 parallel problems. We did the arithmetic. 4.6 divided by 57.5 is 0.080. That's the first part of the problem, the arithmetic. And here's just your scientific notation, 10 to the 12th divided by 10 to the 9th, that's 10 cubed. And then the third and final part, joules per second divided by joules per meter is just meters per second. Now, I gotta say, I was a little disappointed. I thought the number would be larger. But there it is, 80 meters per second, 100 miles per hour. I thought it would be faster. I mean, obviously, the coal trains that are coming, through Missoula, they might be doing 50, 40, 50 miles an hour. The coal plant is not running fast enough to burn those cars just as they're coming in. But if you could imagine three parallel trains coming through Missoula, each going 60 miles per hour, that's all of the global coal consumption is just being burned. All of those just evaporating. That's the rate. That's the global rate. I thought it would be greater, but that's it. So again, just imagine. You could have a single car going 180 miles an hour, or you could have 3 cars doing 60. So let's just draw that out, because that's our final answer. And I'll let you go. So basically, what we're looking at. Choo-choo. 60 miles per hour. Going, and this is carbon, and here comes your oxygen, and then out goes the CO2, H2O, SOx, NOx, etc. Right, so there they are. That's the global coal consumption schematic. Three coal cars doing 60 miles an hour into a. I thought it'd be bigger, but that's it. Seems kind of small when you look at it that way. Maybe the next thing to do when we look at emissions, there's 35 billion tons of CO2 are emitted into the atmosphere per year. You can do the same problem, say how many tons per second are being emitted, because all that carbon is being converted into carbon dioxide. So there you go. I'll launch exam 3, and if you want, go ahead and get started on that first problem set. You know, it's problems just like the one we just did. It's mainly just manipulating units, and you know, the thing to keep in mind is you're always kind of doing the 3 problems at once: the arithmetic, the scientific notation, and keeping track of units. So that's it. See you Tuesday.
All right. Have a nice weekend.
Thanks. I will. You too.